This particular video is picking up from the last one where we were focusing on sampling as we look at digital audio. And as I mentioned before, the idea of converting analog to digital audio is a process that involves two parts that are integrated. They work absolutely together tightly. They're not two separate ideas that happen one and then the other. They're two things that are happening exactly the same time. They're part of the same process. They are sampling and quantization. So we talked about sampling. Now I'm going to put a little focus on quantization. It's important to keep in mind that sampling is intended to capture the frequency component of sound. That's its primary goal, and that's one of the reasons why you see a parallel between frequency measured in hertz and sampling rate, which is also measured in hertz. It's not cycles per second in sampling rate, it's samples per second. But you can see just by thinking about that, there's the parallel between frequency and sampling. Quantization doesn't have quite that same obvious parallel, but the focus here is on amplitude. And we know that amplitude has to do with the energy level, the electrical signal at its peaks and valleys. And so this is going to be focusing on capturing that electrical signal, that amount of voltage, if you will, of that signal that's happening at that moment when we're taking a sample. So let's go ahead and look a little bit more closely at quantization. What is quantization? It's essentially the idea of taking these continuous signals and converting them into discrete digital numbers. So by continuous, we mean it's a wave, right? It's an acoustic signal is a wave in the air, right, in the atmosphere, vibration of the molecules. The electrical signal is an electrical wave, positive and negative flowing electricity. So what we're doing is we're taking this thing that has this continuous flow and we're breaking it into specific discrete parts. And we're taking a measurement of that part using the sampling as how frequently we're going to take the measurement. And the process of measuring it is this idea of quantization. Fundamental part of it is the concept of bits. Binary numbers. So a binary number is 0 and 1. I will frequently point out that we are very used to simple binary systems. In fact, every time I walk in the classroom that we're in, or we walk into our labs, we use a binary switch. We turn the light from off to on to off. It's got 0 for no electricity going to the light, and 1 for all the electricity going to the light. It's on or off. So that's a very simple, basic binary system. Of course, with audio, we're going to have to get more complex than that. But that's a good reference point for us to start from. Now, I want you to think about the idea that we are converting this infinitely variable signal, and we're expressing the idea of quantization in the language of bits, and we think of that resolution as being an X number of bits. The number of variables, or the values that we're capturing, are going to be reflected in the idea that we have two base numbers, right, of 0 and 1, and we can string those zeros and ones together. And the more that we string together, the more variables we can account for. The more, in this case, electrical signal discrete values that we can account for. So let's go ahead and take a look at one of these simple systems, right? A basic sine wave is something that we have been looking at and working with since the beginning of the semester. We can represent that sine wave in 2-bit resolution. So when we talk about a 2-bit resolution, we get the 2 from 0 and 1. So we've got two options. Now, if it's a 2-bit resolution, we've got 0 and 1, and that means we're putting together two 0 and 1 options together. So we can choose 0 or 1 for 1, and we can choose 0 or 1 for the second. And from that, we get 4 different levels or options, 4 different combinations of 0 and 1 together. And here's the greater detail of it. Right? So here we can see that if we have a very simple system, we can have 4 different levels. We can have a 0, 0 level, we can have a 0-1 level, we can have a 1-0 level, and a 1-1 level. So that gives us all the different options, all the permutations that we can make up. If we have 2 bits, that means 2 lines where we can choose to have a 0 or a 1. Now this is, very simple, and it does go back to that basic idea that I talked about in a previous video when we think about word processing and the ASCII code. So remember that we were stringing together binary numbers in order to represent a letter or a number that we use when we're typing and communicating. And this is very much the same thing, except at this point, the thing that we're trying to capture is not this visual image of a letter, but it's a sound, and it's got an electrical property. So we're trying to capture the electrical signal at a particular time, and then hold on to it, map it, and say, at this time we need this signal. Okay, well, we actually, of course, work with systems that are more complicated than a 2-bit resolution system, right? So there's our 2-bit resolution. Once again, we can account for 4 different levels. But if we increase this to a 4-bit resolution, that means we're talking about 2 as our base to the 4th power. And that's where we get that exponential increase in the number of options we have to represent the electrical signal that's passing through. So once again, we'll get into some of the details. If we have a 3-bit signal, digital conversion, then that means we have 2 as our base to the 3rd power. So 2 to the 3rd. 2 times 2 is 4 times 2. And now we've got increased number of options. We've got 8 levels to address and use that to sort of map out our electrical signal. Of course, that's not nearly enough. If we have a 5-bit converter, so it's 2, again, representing the 0 and the 1 in the binary number, but now it's to the 5th power because we have many more combinations of 0s and 1s that we can use to reflect different levels of electricity. So now we've increased to 32 levels. That means there are 32 different electrical signal levels that we can represent in this 5-bit system. Now, you've probably seen the label of like 24-bit resolution, 24-bit. That, of course, means we've got many, many options to represent quite an array of electrical signals going through. Take it on the simple side again, 2 to the 3, which is a 3-bit system, right? 3-bit resolution gives us 8 levels. Let's have an example. This is not, an example based on reality of just manufacturing this for the purpose of display, right? So let's say the voltage is 7 volts. Every time we take a sample and the signal is 7 volts, we will record 111. That would be mapping on a binary number and making it the equivalent of an electrical signal. In this case, we're saying it's 7 volts. If it were 1 volt then that came in afterward, it would be 001. That would be stored for the next sample. And so for every sample we're taking, we're going to have some measurement of the voltage at that time, and we're going to record a number, a binary number, that represents that voltage. So here's where we get to the mind-boggling aspect of it. When we're dealing with simple systems like 4 bits and 8 bits, well, those are manageable numbers and they make sense. But if you think about the numbers of options that we have, say going up to that 24-bit system, well, if we do a 24-bit system, we have 16 million plus options in order to represent the electrical signal at that time for a sample. That gives us a lot of opportunity. And it's important to keep in mind that the greater the bit depth, that means the higher the bits, the bit level, the lower the noise level that we will have in our recordings, because we can isolate that more effectively. So this is our concept of quantization. Remember, sampling and quantization are 2 parts of the same process of converting digital audio to, converting analog audio to digital audio. And of course, when we're converting digital to analog, we're just doing the opposite, the same way we were looking at microphones versus speakers. we're going to actually start with a digital number, and then we'll be representing that number using the signal that we associate with it, the electrical signal that associate with it. And the numbers of those stored digital numbers we have and how quickly they go by within a second is representing the opportunity to have the frequencies evident in it as well. So that's our combination of digital audio. We started looking at the basics, the foundation of digital audio, what makes it beneficial, what are the positives that come out of it, the general system. Then we looked at the two parts that work together, sampling rate and quantization, that are part of this process of the conversion. Keeping in mind, it's really important that this is a simplification of the process. There are lots of details in there. I've got a great video that will show you that idea of the Nyquist theorem, so please check that out. And we will talk about how to work with some of the processing in digital sampling and signal conversion as we move further into the semester.